Previously, you saw how you can start fitting parameters to an equation by making a guess about those parameters, measuring your loss on that guess, and then using what you knew to make a better guess by plotting on a chart of the loss, using calculus to get the gradient, and use that to figure your way out towards minimum loss. This is ultimately how neural networks work under the hood. So now we'll switch gears and see how to code a neural network that achieves the same goal. Recall, here's a set of numbers. We have a bunch of x's and a bunch of y's, and we want to figure out the relationship between them. Earlier, we used the process of machine learning, guessing, measuring, optimizing by hand to get the result of y equals 2x minus 1. Let's now see how a neural network would do this. Here's the code. There's a lot going on here that you may not be familiar with, so I'll break it down line by line. The first line defines our model, and it's the simplest neural network I could think of. You've probably seen neural networks that look a little like this. So that we understand the terminology in the code, let's explore some of that here. Each of these circles will be considered a neuron. And each of these sets of neurons is called a layer. So for example, this would be one layer, this would be another, and this would be yet another. The layers are also in a sequence, and the first layer feeds the second, which feeds the third, and so on. As a result, we will use the term sequential to define this network. You might also have heard the term hidden layers when dealing with neural networks. The hidden layers are the middle ones that are neither input nor output. So the middle ones you can see here is the hidden layer. The neurons are all connected to each other, making a dense connection. And we'll use the term to define the name of the layers. So now if we go back to our code, we can see the term sequential. We're defining a sequential neural network. Within the brackets, we would then list the layers of the neural network. And we have only one entry, so we only have one layer. This layer is a dense, so we know that it is a densely connected network. The units parameters here tells us how many neurons in the layer, and we can see that we only have one. So this code defines the simplest possible neural network, one layer with one neuron. There's one other thing to call out. We are defining the first, and in this case, the only neuron in the network. You have to tell it the input shape. And here the shape is only one value. We're training a neural network on a single axis to predict single y's. So our input shape couldn't be any simpler. Visually, our neural network looks like this. We only have one layer and it has one neuron. It takes an input, which is a single value we'll call x, and we learn the parameters to produce y based on our input data. So now hopefully you can see that we are defining a new model, which is a neural net comprised of a single layer with a single neuron, and the neural net will take a single input value. When we compile the model, we'll define a loss function and an optimizer. The loss is mean square error, as we used previously. But instead of calculating everything ourselves, we just tell TensorFlow to use this loss function for us. The optimizer is SGD, which is stochastic gradient descent. This will follow the process we saw in the previous video of using a gradient to descend down the loss curve and to try and reach the minimum. We're not doing any of the math ourselves, and we just have TensorFlow do it for us. Now we specify the x's and y's. TensorFlow expects these to be in a NumPy array, and that's what the NP stands for. And you can see that the array of x's has the corresponding y for the value in the x's. So y equals -3 when x equals -1, y equals -1 when x equals 0, and so on. The process of figuring out the relationship or training is called fitting. So we do model.fit. We are fitting the x's to the y's. We do this for 500 epochs, where each epoch is a series of steps that we had discussed previously. Make a guess, measure the loss of the guess, optimize, and continue. So this line of code will do that 500 times. Then when we are done, we'll use this model to predict the y of a given x. So if x is 10.0, what do you think y will be? Well, you can try for yourself now. Maybe you think if x is 10, then y will be 19. The answer to that is no. Can you figure out why?